So our today's focus will be on the thermodynamics NCERT theory part 7, this section 5.5. Remember, we have to use the Hess's law of constant summation. So you should be aware about it in all perspectives. This is the disclaimer. Then in this class, our objective would be to calculate the enthalpy change for various types of reaction. So we will see a variation of it, and the most important part in those variations will be their definition. So the definition is the most important part. If you know the definition completely, then and then only you will be able to use them in your questions and numericals. If I map all of these topics according to the NCERT, then first of all, we will cover 5.5, which is enthalpies for different types of reaction, in which we will see the standard enthalpy of combustion, the enthalpy of atomization, then we have the bond enthalpy. So these are the three types that we will study today. So let us start our discussion on these three types of reaction. So the first type that we have seen was standard enthalpy of combustion. So you must remember the representation also, delta CH naught. For the enthalpy of atomization, it is delta AH naught. Then for bond enthalpy, it is delta bond H naught. Then we have lattice enthalpy as well, which is delta lattice H naught. Enthalpy of solution, delta solution H naught. And lastly, enthalpy of dilution. But as I said we will cover the first three, and the rest of D, E, and F will be seen in our next class. So we'll see the standard enthalpy of combustion, the enthalpy of atomization, and the bond enthalpy. So first we will start with the enthalpy of combustion. Now, what is the definition? It's very simple. It is simply the change in the enthalpy when your 1 mole of a substance is going combustion with oxygen. So if you don't write a combustion with oxygen, that is also good. No problem in that, because combustion is itself a reaction with oxygen. Okay, so it is self-explanatory. But still, for our definition, it will help you. Now, the main part of the reaction of the definition is that we are to see the combustion of 1 mole of a substance. Okay, so this is very important, that we are interested in the combustion for 1 mole of a substance, and then only we will tell it as the standard enthalpy of combustion. Okay. Now, all of your reactants and products, they should be present in their standard state. It's very important because this is standard enthalpy of combustion. Now, what is the standard state? Now, this is quite arguable cheese, right? Why it is arguable? Because you are to define the temperature. In some cases, you see that if you are symbolizing the standard state, then you are already telling the temperature. But if I talk about it in the deep manner, then it should be mentioned along with the temperature. So your standard states should be present along with the temperature. You will get this thing with the help of an example. What is the example? So this is the representation. We have seen it already, delta CH naught. So it is just for your notes. So the example is for the combustion of butane. So this butane is an important component of your cooking gas. Now, if this butane is undergoing the combustion, what will it produce? Since it is a hydrocarbon, it will produce two things definitely. What are those? One is carbon dioxide and the second is water. The second important thing in this reaction is that it is a balanced chemical equation. And to do the problems of thermochemistry, it is very, very important that you balance the chemical equation. This is the most important part. Okay. If you know it, then how do we use it to define the combustion of butane? Or I would say the standard enthalpy of combustion for butane. So this value is given as minus 2658.0 kilojoule per mole. So three things are verified from it. What are those things? First is, we are getting the combustion for 1 mole of gaseous butane. Okay, you can see that the butane has a coefficient of 1. So this is a strong requirement for the standard condition that your combustion should take place for 1 mole. Then the second thing is that all your reactants and products, if you look at the butane, if you look at the oxygen, then they are present in their standard state, which is gaseous. And the third point you will notice that the combustion is an exothermic reaction in this case. And this is true for all the cases. So all of your combustion reactions are always exothermic. Okay, so remember this point. Exothermic means they have a negative value of enthalpy or the system releases heat. Okay, the net release of heat is seen in the case of combustion process. So 3 points are there and you should remember it. It's very, very important. First is there should be combustion for 1 mole. Second is during combustion, the reactant should be in their standard state at a specified temperature. And the third thing is all the combustible processes are exothermic in nature. I hope this standard enthalpy of combustion is clear to you. Now, let us move on to the second type, which is standard enthalpy of atomization or simply enthalpy of atomization. Now, again, I said it that the definition part is the most important part. So first we will see that thing. Definition says that your enthalpy change for atomization is simply the breaking of 1 mole of a bond to obtain the gases to obtain the atoms in the gas phase. So 3 things are important here. First is you are to be breaking 1 mole of bond. Okay, you will always break 1 mole of bond. So first thing. Second thing, the product should be obtained in the atomic form. And third thing, your atomic form should have a state of gas. Now let us try to exemplify this same thing with the help of a reaction. Of course, the representation is delta AH naught. So let us take the atomization of the hydrogen molecule. You can see that our hydrogen gas is undergoing a process in which we are breaking the molecule into its atom. And the atoms are what? The atoms are hydrogen atoms. So hydrogen atoms are formed by breaking 1 mole of hydrogen-hydrogen bond. Why I am saying it as 1 mole? Because your hydrogen has a single bond between these. Okay. Now this definition will put you in difficulty for the case of those molecules which have multiple bonds. So the true definition should be like this, that it is the energy which is required to break 1 mole of a diatomic molecule. Okay. And we are unaware about the type of bond. So let us just try to specify this reaction with the help of the definition that we have. The first thing is already verified that we are breaking 1 mole of bond. And second thing is that your hydrogen atoms are formed and those are in the gaseous state. See, we are putting a G against this hydrogen. Therefore, your given reaction is the enthalpy of atomization. So this enthalpy of atomization is itself self-explanatory, because again, we are converting our molecule into atom and therefore we are calling it as enthalpy of atomization. Moving on further, we can take one more example. Suppose we are taking the methane molecule. Okay, we are taking the methane molecule. Then what is the enthalpy of atomization? Again, here we are breaking 1 mole of the methane. So what we are specifying here? We are specifying the molecule as 1 mole. Got it? Now, when it will atomize, what it will give? It will give 2 things, carbon and hydrogen. Now, carbon will have a coefficient of 1 because only 1 carbon is present on the reactant side, and the hydrogen will have a coefficient of 4. And the process is releasing a heat of 1665 kilojoule per mole. Now, how can we just validate this through our definition? The first thing is that the only products that we obtain are atoms and no molecules are there. This is the first thing. and they are present in the gaseous phase. Now, let us talk about a very interesting example. What is that interesting example? So, that is sodium solid. Now, what are we doing in this process? We are converting our sodium solid into sodium gaseous. Now, why are we not saying it that the sodium is already present it in the atomic phase? Why are we breaking it further or putting it in the gaseous phase? Because our definition says that atomization will only and only take place when the atom is present in the gaseous phase. So atom to be converted into gaseous phase, we are to give energy of 108.4 kilojoule per mole of the sodium solid. There is an important point here. What is that important point? For all of these cases, what you see for the hydrogen, if you consider, or for any diatomic molecule, if you consider, your enthalpy of atomization is equal to the bond dissociation energy. Now, we have not talked about this. We will discuss this later on. But before moving on further, another point is given. What is that point? That your enthalpy of atomization is equals to the enthalpy of sublimation. Why are we saying it? Because here we are converting our sodium, which is present as 1 mole and in the solid state, directly to the gaseous state. Now we know this process. This process is sublimation. And since we are keeping our mole as 1 and we are converting it into the gaseous at a specified temperature and standard state, therefore, in this case, your enthalpy of atomization is equals to the enthalpy of sublimation. We have already seen this notation, okay? So why the equation is so? Because the solid atom is directly getting converted into the gaseous atom. Moving on further, we have our next type of reaction, which is telling us the bond enthalpy. So we'll discuss about this. Now, what is this bond enthalpy? It is basically telling us the enthalpy change when we break a bond. So remember, this is related for the breaking of bond. If you are considering it for the making of bond, then the value will get opposite to the value that we have already. So our chemical reaction is evolved from the breaking and making of the chemical bond. So the energy that is required to break a bond and the energy that is released when a bond is formed is related to this bond enthalpy. How do we represent it? Very simple. Delta bond H. And this chemical bond energy can be classified as 2. Now, why we are classifying it as 2? We'll see it later. We have not seen a classification of the enthalpy before this. We are seeing it for the first time. And there is a very specific reason for it. Now, first, let us focus on these two types. First is the bond dissociation enthalpy. And the second is the mean bond enthalpy. First, let us discuss about the bond dissociation enthalpy. So, it is the enthalpy change when you are breaking 1 mole of covalent bond of a gaseous covalent compound into its product. And the product are in the gaseous phase. How? Let us try to understand this. Suppose we are taking the case of H2 again. So what we were doing this in this case, we were breaking 1 mole of bond. And what we were getting? We were getting the hydrogen atom. Now you will say that isn't it similar to the atomization case? Yes. In this case, it is similar to the atomization. So what you can say that for the diatomic molecule, the enthalpy change of the process is the bond dissociation enthalpy of HH bond, and it is equals to the atomization of dihydrogen. Now there are many cases in which the bond dissociation enthalpy is equals to the enthalpy of atomization, and these cases are related directly to the diatomic molecules. For example, if you are considering the bond dissociation enthalpy of the diatomic molecule chlorine, then this value is equals to the 242 kilojoule per mole, and it is equals to the enthalpy of atomization, because here we are converting 1 mole of chlorine molecule into its atoms. Now we can also consider one more example. Suppose we are breaking the oxygen-oxygen double bond. So this is bond dissociation enthalpy for the oxygen molecule, and since we are converting our oxygen molecule into 2 oxygen atoms which are in the gaseous phase, so in this case your bond dissociation enthalpy is also equals to the enthalpy of atomization. I hope this is clear to you. Okay, so this is very important distinction here that has been made, right? Moving on further, why do we need the mean bond enthalpy? Now the question arises. We are happy with the bond dissociation enthalpy. We are calculating our values, very good. But the problem is that when we are to break a particular type of bond which is present in more than one type, then we take the average amount. How do we take it? Let's see. So it is basically the energy which is required to break multiple bond in case of polyatomic molecule. So in this case, what happens? If we suppose we take the case of hydrogen, okay, so it has a single type of bond. If you break that bond, you got your hydrogen atom. But if we take the case of water and we start breaking the bond, so first OH bond will be broken and we will get a hydrogen and a OH species. Very good. But if you break the second OH bond, then it will not be the same, because the environment is different. If you consider a simple water molecule, it has oxygen and on both sides we have 2 hydrogen. But if you are taking a OH which is being produced after the cleavage of one OH bond, then we are getting a different kind of structure. Therefore, we will need different type of energy to break that same bond. How do we understand it? So for polyatomic molecule, we are to be in need to define a new kind of bond dissociation enthalpy, which is mean bond enthalpy. Because the bond that is broken, it results in 2 species that are having a different structure. So you may be facing problem in this mean bond enthalpy. So this will be clear when you will see another case of a different polyatomic molecule. For that, let us take the example of methane. So in first sight, you will notice that all the 4 CH bonds are equivalent, but they are not equivalent. How? So if we break the first bond between the carbon and hydrogen, so that bond dissociation enthalpy is plus 427 kilojoule per mole. So what do we get? We get a CH3 and a H. Okay, so this is for the breaking of first CH bond. Next, if you break the next CH bond, what you will get? You will get CH2 and H. Is it clear? Now, if you see that bond dissociation enthalpy, so it is completely different. Now you have to give a greater amount of energy, which is 439 kilojoule per mole. So this is the change. Although your 4 CH bond may look identical, but they have different values, because once you break one CH bond, you see a different environment. Now your carbon is surrounded by 3 hydrogen atoms. Right? So to break one more H from the CH3, you will need a different amount of energy. Now, next, you have to break it further, CH2 to CH, to get the H here and CH, and further one more bond is to be broken, which will give you the carbon and hydrogen. So you can see it very clearly in these 4 steps that your bond dissociation enthalpy is changing for each bond. So 4 CH bonds were there, and although they were identified as identical, but they have different bond dissociation enthalpy because of the different environment. You can just try to break each of this bond individually and you will notice the different environment. So I'm leaving this task onto you. Just try it by yourself. Now the question arises, what is the result of this different bond dissociation enthalpy that we get for the successive CH bond? The result is that for this case, if you want to calculate the bond dissociation enthalpy, rather than taking one value, we take the average for all of these. Okay, so what we do, we add all of these values and divide it by 4. So 4 CH bonds were there and 4 values were there for each of this. So we add all of these 4 values and divide it by 4 to get the mean CH bond enthalpy as 416 kilojoule per mole. Now, if someone asks you, what is the bond dissociation enthalpy? You will simply tell it as 416 kilojoule per mole. Why? Because we have to take the mean and not the value for any individual breaking of CH bond. Now, a second important derivation here. What is that realization? If you add these 4 equations for the 4 successive bond, you will see that CH3 and CH3 will get cancelled out. It is on the opposite side. CH2 and CH2 will get cancelled out. CH and CH will get cancelled out. Right? The only thing that will be present in the reactant will be your methane molecule. On the right hand side, we will have one carbon atom and 4 hydrogen atom, because 4 hydrogen atoms are there in each of this. One are present on each of this. If you add, you will get 4. And on the right hand side, what we will get? We will get the enthalpy change for the overall process. And what is this overall process? Can anybody identify it? What is this overall process? So what are we doing? We are converting the methane molecule into its atoms. And those atoms are present in the gaseous phase. So, is it looking identical to any other definition that we have seen till now? Yes. So that identification is related to the atomization. So what are we doing here? We are converting our methane in the overall process into the carbon and hydrogen atom. Okay. Now, this is also a direct application of the Hess's law. So what you can do, if you want to calculate the enthalpy of atomization for the overall process, you will simply add all of these to get your desired equation. So this is your desired equation, and these are the given equations that we have. So for this case, we can write a direct relation. So it is only valid for this case, which is enthalpy of atomization is divided by 4 to give us the enthalpy of bond dissociation. Okay, or mean bond enthalpy simply. Is it clear to all of you? So this is very, very important. So if I talk about the thermochemistry part, this is the most important part in the thermochemistry, which is related to the bond dissociation enthalpy. Now moving on to the next, how do we apply this reaction enthalpy? How do we calculate the reaction enthalpy using the bond dissociation energy? For that, let us take an example. Suppose we are having a gaseous phase reaction where our hydrogen and chlorine are reacting to give us 2 moles of HCl. And we are given with the bond dissociation energy for each of this. So for the hydrogen, it is 436. For 1 chlorine, it is 242. And for 2 HCl, it is 2431. 2 multiplied by 431, which is 862. So all of these values are given in kilojoule per mole. Suppose you have all these values and you are asked to calculate the enthalpy of reaction. So you have the bond dissociation enthalpy of hydrogen, you have the bond dissociation enthalpy of Cl2, and you have the bond dissociation energy for HCl as well. So it's a very simple formula to calculate all of this. What is that formula? So it says that the enthalpy of reaction can be calculated in terms of bond dissociation energy, in which we subtract the bond dissociation energy of product from the bond dissociation energy of reactant. So this is opposite case from our natural instinct. So our natural instinct says that if you want to calculate the enthalpy or something like that, you always subtract product from the reactant. But here notice this is very, very important. If you want to calculate the enthalpy of reaction in terms of bond dissociation energy, you are to be considering a different formula, which is bond dissociation energy of reactant minus bond dissociation energy of product. Now, why are we doing it? What is the logic behind it? Is there any logic? Yes. That logic is the value that you have is for the dissociation. And we know that the molecules which are present on the right hand side are not getting dissociated. That means your products are not getting dissociated. On your product side, we are seeing the formation of bond, not the breaking of bond. Therefore, we are putting it with the negative sign. Whereas for the reactant side, we are seeing the dissociation. So we take the value as it is. I hope this point is clear to you. It's a very good logic to explain it. Again, I am repeating it. So bond dissociation energy means what? You are giving the energy to break a bond, but the bonds are broken on the reactant side. So we take the value as it is. But the product side is requiring the building of bond. So rather than taking the bond dissociation energy of product, we take the negative of it. And therefore, we are getting this formula. If this is clear, this formula is clear, let us apply onto the above example. So simply add both of this for the hydrogen, hydrogen and chlorine, chlorine, which are on the reactant side. So 436 plus 242 will give you 678. Then for the HCl, we have only one kind of species, but that are present in 2 mole. And it has a value of 862. So let us put it on the negative part, right? If you do this calculation, you will get your enthalpy of reaction as minus 184 kilojoule per mole. Is it clear to you? It's very simple and very important at the same time. So it's a good news for you. Something which is simple and important, right? So your bond diffusion enthalpy is the most important part of your thermochemistry. I'm repeating this part again and again. Now, an important note here. So this thing that we are getting, the reaction enthalpy that we are calculating from the bond dissociation energy, it is an approximate value, right? And you can use it in your numerical, no problem. But for your scientific determination, you must know that these relationships that you are seeing are not the practical ones. It is just the approximation. Okay, clear? Now let us summarize all of this. So first, what we saw the standard enthalpy of combustion. What it is? It is that heat which is released when 1 mole of a substance is getting combusted with oxygen, or you can simply say it is getting undergoing combustion, and it will be always exothermic. Second point, what is enthalpy of atomization? Enthalpy of atomization is the conversion of a molecule and 1 mole of molecule into its constituent atoms that are present in the gaseous phase. Third thing, what is bond enthalpy? Now, bond enthalpy is the energy change when we break or form a bond. Now, for the forming of bond, we will take the negative sign, and it includes 2 types. Bond dissociation enthalpy, which is for a specific bond, for a diatomic molecule, I would say directly. For the polyatomic molecule, where we have the same kind of bond, but I would say in multiple times, then in that case, you have to take the average. Okay. Do not take the average value for the double bond. So that's a different thing. When you considered the case of CH4, you saw 4 different bonds. Okay. You didn't see 4 bond present at the same path. Okay. You saw 4 different bonds. If you see oxygen-oxygen double bond, then you can't take the average of 2 single oxygen bond and calculate it for the double. For double bond, you have to take a separate value, and that is separate, right? And the last thing, you can calculate the reaction of enthalpy in terms of the what? In terms of the bond dissociation energy, and that is reactant bond minus the product bond. So this was all from the theory part. So just wait for a while. I will switch on to the DPPs. Just wait for 1 or 2 minutes. Okay, so here is your DPP part. So there will be 5 questions, and we will get approximately 8 or 10 minutes to solve it. So let's start this first question. Which of the following statements about the standard enthalpy of formation is correct? The first one is, it is the enthalpy change when 1 mole of a compound is formed from its elements in the standard state. First one. Second is, it is always positive for exothermic reaction. It can be measured directly for all compounds. It is zero for all elements in the standard state. So what is the correct statement? So we have to discuss about the standard enthalpy of formation. Okay. So what you would say for this question? First of all, this statement is absolutely incorrect. It is never positive for exothermic reaction. It is negative for exothermic reaction. It can be directly measured directly for all compounds. No, it is not correct. You have to use the equations. Then it is the enthalpy change when 1 mole of a compound is formed from its element in their standard state. Is it correct? Yes, it is correct. It is zero for all elements in their standard state. So the correct answer will be the first one. Next question. For the reaction calcium carbonate dissociating into calcium oxide and carbon dioxide, the standard enthalpy change is calculated as, how we will calculate it? Here we are calculating it in terms of the formation. Okay, we are not calculating in terms of bond dissociation energy. We will not use that logic. We'll use a simple thing which is product minus reactant. So calcium oxide plus carbon dioxide. Okay, so this will be added for the product part minus the reactant part, which is calcium carbonate. So standard enthalpy of formation of calcium oxide plus the standard enthalpy of formation of carbon dioxide minus the standard enthalpy of formation of calcium carbonate. So this one is the correct one, product minus reactant. Next question. Next question says that the standard enthalpy of vaporization, delta vaporization H naught of water at 373 is 40.79 kilojoule per mole. What does this value represent? So what do we have here? We have the standard enthalpy of vaporization. What is happening in the standard enthalpy of vaporization? Your 1 mole of water, which is present in the liquid state, that is getting converted into 1 mole of gas of water. And for this process, your delta H, which is simply as delta H vaporization, I would say, is given as 40.79 kilojoule per mole. So this is our whole situation. Now, what does this equation represent? That is your question. First is heat released when 1 mole of water vapor condenses. Is it correct? No, we are not condensing it. We are vaporizing it. And in that process, the heat will be consumed. So it will have a positive value. It is being already told to you in the theory part. So this is absolutely incorrect. Then what is the next thing? Heat absorbed when 1 mole of liquid water vaporizes at 1 bar. So this can be correct. Let us look on the other options. Heat released. Is it correct? No. I have said it to you already that the vaporization process requires heat. So it will never release that heat. It will always absorb that heat. Last one, heat absorbed when 1 mole of ice melt. So this is for the fusion process and not for the vaporization process. Therefore, our correct statement will be the second one. Got it? Is it clear? Moving on to the next one. So, for the reaction in which H2 plus Br2 is giving us 2HBr, the enthalpy of reaction is minus 72.8 kilojoule per mole. Then what is the enthalpy of formation of HBr? Now, this one is a very good one. How do we solve it? We know it already that the enthalpy of reaction can be written in terms of enthalpy of formation. How do we write it? Enthalpy of formation. So let me take the standard state as it is mentioned in the question. So standard enthalpy of formation for the product, which is HBr. And HBr in which state? in the gaseous state. So the state is also important. And this thing will be multiplied by 2. Why? Because we have a coefficient of 2. Then next what we have? We have it for the reactant. But if you see, then both of these reactants are present in the standard state. And we know it already. If they are present in the standard state, therefore its enthalpy of information will be taken as 0. Right? It will be taken as 0 for both of this. Hydrogen molecule also and bromine liquid also. So hydrogen molecule is present in the gaseous state in the standard state, and bromine is present in the liquid state in the standard state. Now we have this value already. It is minus 72.8 kilojoule per mole. If you divide this thing by 2, we will get the enthalpy of formation for the HBr as well. That is in the gaseous state. What value you will get? So 2 3 is 6, 2 6 is 12, 2 4 is 8. So this will be your final answer. And this will be present in negative form, right? So it's very obvious. So the correct answer will be the second one. Do you have a doubt in this question? Is it clear to you? So anyone who has a doubt in this? So many of you are attending the session. So you can ask your doubt without any hesitation. Is it clear to all of you? So Devansh, Riya, Joshua, Ranjit, Umarpreet. Anyone who has a doubt in this question or any other question that we have attempted right now? Okay. So I guess it is clear to all of you. So this was all for today's session. We have covered the part. So our tomorrow's part will be the same, the enthalpy of reaction. But one important point here. You have to be clear about this Hess's law of constant summation. And we will use it to and fro. The only way to, you can say, master it is to practice the problem related to it. Okay. So thank you for attending the session. I hope you enjoyed it.